So the next talk today is Mariami from legal. We're talking about hypergraph states and entanglement and robustness properties.
Hello everybody. Thanks to the organizers to give us a chance, and especially to Ross for bearing with me when I needed to get a visa. It's a painful process. So I'm Mariami. I'm working with Professor at the University of Siegen, and also Konstantina works with us. But we have a collaborator in Georgia, Tbilisi, and we are working on hypergraph states. So my talk will be based most of all on the paper which appeared in PRL recently. It's called Extremization of Local Realism in Quantum Hypergraph States. So when this paper appeared, Phys.org decided to feature article about it. So it was quite an epic article with a lot of reads from the people who understand nothing about quantum information or physics. So I chose some of the comments they had. So they are quite amazing. Like if you look at the first one, I'm not going to go through all of them, but they said quite a brutal things saying about it, but the best and the winner of it is the following, which says that physicists find extreme violation of local realism. So that's how they actually give us thinking, and they said looks they find. So yes, that's how they imagine us working on this project. So, okay, this was a brief motivation to listen to us, so that if you meet some of them, you tell them that this is not it. But actually, to tell you the real motivation why we are working on this project is the following: that there is a lot known about graph states, but why do people work on graph states at all? This is a crucial question, because you know that Hilbert space is huge, and you cannot reason about state space entirely. You have to limit yourself to some elegant model of Hilbert space where you can describe your states nicely, and then you can say some general statements on this model only. So a lot of work has been done on graph states in this sense, and we have seen that they're very useful, they're very nice, and I'm going to briefly introduce, and there's some experts in the audience who have worked a lot on this field. So then, okay, we know a lot about graph states, so can we generalize these results? What else comes out of it? So I'm going to talk about hypergraph states in this sense. Then graph states are connected to local stabilizer, as many of you might know. And then hypergraph states are non-local, correspond to non-local stabilizer. Then I'm going to talk about hypergraph entanglement and robustness properties, but to compare it with something, I'm going to compare with graph states and to say, why do we work on this? Because they have some concrete advantages while working on. And then I'm going to talk about some local Pauli and local unitary equivalences between graph states, and then extend it to the hypergraph states. And last will be the outlook. Okay, so what are the graph states and why to study them at all? So as you might already imagine, that graph states correspond to some graphs, where every vertex is some plus state, so it's a X basis state, and every edge between them is an entanglement gate, which is the extended controlled Pauli Z, you can say. So what does it do? You look at the graph, so you write the plus states right here. I don't know if you see the point, actually. You write the plus state in the superposition of 5 qubits, let's say in this concrete case, and if there is an edge between two guys over here, then you apply this entanglement gate. Of course, I omit all the identities. So if there is no edge between 1 and 5, you won't have this entanglement gate, which will be C1, 5. So then you write you apply this entanglement gate, and you get the graph state coming out. So now you ask the question, what are other properties of graph states, or other alternative definition, and it's called stabilizer formalism. So what does the stabilizer actually tell us? So it's an alternative way to write a graph state in the following way. Let's say for every qubit in the plus state, or every vertex, alternatively, you can write it down an operator. Operator looks the following. You look at the first qubit, you write down Pauli X, and then you look at the neighbors of this qubit, and you write Pauli Z in second qubit and third qubit. And then this is called a stabilizing operator. You can do the same for second qubit. You look at the second qubit, and you look at its neighbors, it's 1 and 4. So you analogously write down the stabilizing operator. So if you continue and write it down for every single qubit, then you see that it's a property of stabilizer that the graph state, which we already wrote, is an eigenstate, unique eigenstate of all these stabilizing operators with a +1 eigenvalue. So you can already say that this stabilizing group is graph state. So it's a very nice property in the sense that you can look at a lot of non-locality proofs concerning the graph states. Okay, now having said this, I'm going to jump to some applications, and we already heard that they are useful for measurement-based quantum computation, and it's actually true, and there is this nice paper from Robert Rausendorf, and also Hans Briegel will be here shortly also. Also then, already we have heard that GHZ states are useful in the talk yesterday, and we heard that if you have a GHZ state here and if you allow the control computer, which can make measurements on the GHZ state, but control computer can only have the XOR power, then by making the measurement on 3-qubit GHZ state, you can boost your power to computational power in control computer to full classical computations. And we also know the next application is that they're useful for some codes, so for coding theory. So I hope that you're all convinced that graph states are good. But now we have to move to hypergraph states because our time is limited, or we can go on the graph states for a very long time. So hypergraph states, I introduced graph states because hypergraph states are explained or described very similarly to them. So they correspond to hypergraphs. So how hypergraphs generalize the graph states is the following, that you don't allow only two edges, but you allow these weird edges coming in also, which connect more than two vertices. So let's say if in graph state you only had this kind of edges, which is 4 by 4 matrix, which corresponds only 2 power 2 by 2 power 2 connections. Here this is not the case because you have, let's say, this green edge, which will correspond to 8 by 8 matrix, which means 2 power 3 by 2 power 3 matrix because it connects 3 vertices, and it has all ones on the diagonal and -1 in the end. So what you do is that you again write all the states in the plus state, and then you apply all the entanglement gates, which now vary in the dimension. Some of them can be 4 by 4, 8 by 8, or let's say on this violet edge will be 2 power 4 by 2 power 4. And then this you might have some just like single gate as well. So in the sense it's more general. You already see that it's way more general plus the graph state. So now we ask, what is the simplest case? So to have a hyperedge, you should have 3 qubits to draw a hyperedge. And this is the simplest example. So this is this 8 by 8 matrix applied to the full computational basis with an XZ basis, and this is the state corresponding to it. So now we ask a question, can I write the stabilizer formalism? So for this concrete case as well. And this is indeed the case, but if you here had an only local Pauli stabilizer, this is not a case in hypergraph anymore, because you look at the vertex 1 and you look at its neighbors, but how do you define the neighborhood anymore? It's not a local neighborhood. You have some global neighborhood coming in, and then you write down x1, and you have these bigger gates. So this is a non-local stabilizer. You can do the same for H2, where this corresponds to Pauli X, and then you have C1Z, which is again a non-local control Z gate coming in. But it's a nice property that even in this case, you still have the property that hypergraph state is an eigenstate of non-local stabilizer. And this stabilizer is not Pauli stabilizer anymore. So now, what can we do about this? I mean, can we say anything on this concrete state, only looking at its stabilizer? And the answer is yes. So what we can do, we can write down this stabilizer, just it's a rewrite, and now we can ask the question, can I deduce any perfect correlations? Because if I have some perfect correlations, as we heard in the previous talk, then you can say something about non-locality proofs. So indeed you can say you can deduce the following probability. Now let's see how can you guess this probability. So this is the probability if you ask a question, what if I make a measurement in x direction on the first qubit over here, and in z and z direction in second and third qubit, what can I not get as an outcome? This is what you ask the state. And if you make a measurement and if you get plus outcome here in x direction, but if you make a measurement in z direction, that you will end up in -1, and then plus times minus will give you minus, but you always know that this hypergraph is a +1 eigenvalue, eigenstate. So then you deduce that this is a perfect correlation which you can never reach in the hypergraph state. Now you ask a question, can I say the same if I measure minus here? What can I, if I measure minus in x direction, what can I never measure in z direction? So if you measure minus here, as you might already guessed, you must measure minus here. So then you are bent to get any correlations from these guys, and then you just write some perfect correlations. So coming from the first stabilizer, you already have 4 perfect correlations, but this is again only for first one. So what you can do, bless you, this is the symmetric state. So what you can do, you can just permute these correlations, and then you have 12 perfect correlations coming in already from this simple hypergraph. So not to bore you too much with this and to go on more exciting things, what you can do, you can just take these correlations, assume a deterministic local hidden variable model, and then you take all of these and you get some certain probability which is not in the support. And as we heard, and then you can see that this is not the case in hypergraph state, and then you already derive some contextuality argument. We heard a lot about strong and weak contextuality yesterday, and this exact state corresponds to functional dependent state, which appeared in Abramsky et al. Paper, maybe last year. So this is also done in there, but they didn't connect this to any hypergraph state back then. So it's just a different representation that they used. What you can do, you can also go on and write a similar model for not fully local hidden variable model, but for some more restrictive model, which is 1 is local and 2, 3 have no signaling. And you can use the same argument exactly, and without boring you much, you can go to some contradiction again. But this is not a Hardy argument anymore, but it's some kind of a Hardy type argument. You can see that if you restrict yourself to this model, then you can never measure these 2 probabilities simultaneously. I mean, you can never predict your local hidden variable model will never predict you these 2. But you know they are true in hypergraph state, so you can then, they are symmetric, permutation symmetric, so you can take mixture of all bipartitions here, and then you can write down some genuine multipartite Bell inequality. But again, this is for 3 qubits. Okay, now let's forget about this. We already learned that 3-qubit hypergraph state is non-local. It's genuine multipartite entanglement. So now what can we say for general hypergraph states? How entangled are they? So we asked the following question, and for this we need to compare this with something we already know. So we compare them with GHZ states. So GHZ state, as many of you know probably, correspond to fully connected graph state. Correspond means that they are locally equivalent, locally unitary equivalent to fully connected graph state. So let's say instead of GHZ state, now I look at the hypergraph state and I want to compare their properties. But how do I generalize this? What is my principle to generalize is that I look at again GHZ state with a fully connected graph state. But instead of this, now I want to also look at fully connected hypergraph state, where every edge connects exactly 3 vertices. So, and I call this fully connected 3 uniform hypergraph state, because I restrict every edge to have only 3 vertices in it. And then I ask, can I go in n qubits? Okay, I didn't draw n qubits fully connected hypergraph state because it would be quite nasty to draw. And I have to choose an n, so this is also a difficult task. So what we can do, instead, we can look at what we know already on GHZ state. And on GHZ state, we know that if you take a certain Bell operator, which is the Pauli Bell operator, and if you apply this Bell operator to the GHZ state, and you calculate what is the maximal classical value hidden variable model can give you, and what is GHZ state attaining, you can easily see actually that GHZ state always gives you 2 to the power n minus 1, but the classical value is exponentially lower. So you already know that you have exponential violation of some kind of extended Bell inequality. Yes, extended Bell inequality. But this is called Mariami inequality. It appeared in 90s, so it's quite. I wasn't born yet when it appeared, so it's quite old Bell inequality. So what we do, we take exactly same, a bit modified tilted Bell inequality only in one of the bases, and then we apply the same to the hypergraph state. But there is no reason why hypergraph state should give us the same exact violation, because it's not an eigenstate to local Paulis anymore. Because it's not a local stabilizer operator, it's state itself, but we get the quite similar violation. But actually proof is not a half page anymore. If you look at the proof, it's like 28-page, ugly, nasty, combinatorial proof. This is our result, but we didn't stop here because it was, we were curious whether you can continue doing on this and what kind of violations you get if you take 4 uniform hypergraph states. So you increase the size of the edge, and we indeed see that the violation is actually again increasing. Then we went to 5 uniform, but the proof is also exponentially longer, so we decided not to do an analytical proof for this. So now we ask a question, if it's a similar property, why to do it at all? I mean, if there is a simpler case, why to bother ourselves to go to hypergraph states? But actually hypergraph states give you certain advantages, which is actually connected to this detection efficiency as well, in the sense that GHZ state, which we know that it's highly entangled state, if you make certain measurement, but if you don't have a perfect detection, and if you lose certain particle, your GHZ state becomes a fully separable state. So it's a classical state you cannot use for any quantum information tasks. But this is not the case for, let's say, this concrete hypergraph. You can even trace out number of particles and you still get exponential violation of inequality, let alone that you become fully classical. Even if you trace out half of the qubits, you still are left with certain quantumness. So it's quite an intriguing and nice result because to some sense it looks like a GHZ state, but it reveals to W state properties as well. So it's somehow in the middle. It's highly entangled, but still locally, it's still robust under these properties. So I don't know, any questions for now? Maybe I'm going too fast.
Is the 3-qubit state, as it's
GHZ state.
it's a GHZ
Yes.
equivalent?
Yes.
Did you have an example earlier where it said it was a Svetlitsny type inequality? Is that right? You had
Sorry?
like a slide maybe 4 or 5 slides ago where it was like a Svetlitsny.
Yes.
So you have something which gives you, like, which is on the face of the non-signaling polytope, but for a Svetlitsny type scenario. Is that right? Where?
Yes, and it's actually, you are right, and it's connected to your result, that it can be used for non-adaptive measurement-based quantum computation,
cool.
where you show it.
Okay.
Yes, if this is what you want
This
to
is
do.
not a setup.
So actually he has shown that if you reveal such a violation of similar kind of inequalities, then you can use such states for some computational bootstrapping certain measurement-based quantum computational tasks. And then it directly falls out that it's useful also for quantum metrology. But because it's more robust, it can be better than GHZ states, if you can make these states, of course. Okay, so now I have to quickly move to a bit different task. So we already got that it's highly entangled states, but now we are interested whether which ones are equivalent to each other. So in graph states, a lot of things have been done again by some experts in the audience that you can say which graph states are equivalent to each other by applying some local complementation rule. So it's a following rule. If you apply square root of x here, which is a Clifford operator, and square root of z its neighbors, what this rule does, it just complements the neighborhood. So if there was no edge, it creates an edge here. If there was an edge here, it makes it disappear. So then these two graphs are equivalent to each other under local Clifford. Well, this is just an exercise. If you want to take a look yourself, it's exactly the same rule, but applied to a different qubit. But this kind of thing can be done in hypergraph state only using local Paulis. So if you apply Pauli x here, it gives you a new edge. If you apply Pauli x then here, it gives you a new edge in the neighborhood. In 3 qubits, there is only one equivalence class of hypergraph state, but if you go in 4 qubits and you do an exhaustive search, your computer explodes. So this is an exhaustive search, and you can learn that all these are equivalent under local Paulis. But then you don't want to go on to 5 qubits and look at all possible combinations of 5 and 6 qubits, so you want to do a smart search. So one way to do it is to take this, it's a smart cheating way, is that to take just this rule and try to extend it to hypergraph states. So what you do, you apply square root of x here, and you apply this non-local gates in the neighborhood. And what this gives you, it gives you a new complementation, new way of complementing your neighborhood. Now you can say that this is not a local complementation because I apply some non-local gates. It must change some properties, entanglement properties, and you are right. I have a more difficult example, but I'm going to skip this, maybe skip this example and just look at this one. It's the following thing, that if you apply this kind of operation twice on 2 qubits, these non-local gates can cancel each other because one comes with minus sign, this CE gate comes with minus sign, this from here it comes with plus sign, they cancel, and you get strictly local map, which gives you some new hyperedge. And from here you already know that in 5 qubits, local Paulis are not enough to exhaust all the local unitary equivalences. Then you can continue and play this game and you can get some nice drawings. If you apply on many more qubits, you get some 4 edges, and there are a lot of things that come in with this. So that's where we are right now, and let's see what we have done. So we saw that graph states are elegant. We saw that definition of hypergraph states and their stabilizer, and I believe they're elegant. We also looked at their entanglement and robustness properties. We saw applications. We saw local unitary classes, but now we are interested what comes next. So what do we want to work on? The first thing what we want to generalize is that to look at some well-known graph states, let's say these kind of graph states, and to see what are the corresponding hypergraph states. Next one is to look at maybe cluster states. We know they are useful, and we want to look at the cluster-like hypergraph states and see whether they are also used for universal measurement-based quantum computation and things like this. Second thing we want to do, we want to calculate some kind of entanglement measures, but we don't want to shut up and calculate. We want to actually look at the hypergraph state, use the colorability properties or certain hypergraph theoretical properties and say that, oh, this has this kind of entanglement measures, or we can somehow upper bound, lower bound entanglement measures without actually writing down what the state is. Then we want to do an experiment and show that you can actually make a hypergraph state, and we have some collaborators who are already working on this, and let's see what comes out. We want to extend local equivalencies because in graph state it's known that local Clifford is enough for up to 12 qubits, if I remember, but on 32 qubits or 31 qubits it's shown numerically that it's not enough to cover all the local unitaries. Local equivalencies, but we have a clear picture how to show this will happen sooner in hypergraph states, and from this we want to get some clear idea on graph states as well. If we can get some smaller graph state where we can show that local Clifford equivalence is not enough to show that these graph states are actually local unitary equivalent. Then we want to reason about their stabilizers, whether you can classically efficiently simulate. There is some work done on monomial stabilizer formalism, and we suspect that the answer is no here, so this is way more complicated stabilizer than local Pauli. And we want to, first of all, and most importantly, think about applications. So actually, it has been already shown by Akimaza and Jacob that hypergraph states are used for, yeah, I'm finishing, so it's used for measurement-based quantum computation. So it's not a hypergraph state here as he draws, but he really means here some kind of 3-qubit hypergraph. So he draws it as a triangle just to confuse everybody that it's actually a hypergraph, not a hypergraph. So he shows that you can actually make certain measurements and you can use it as a universal resource for measurement-based quantum computation, and then this state has a really non-trivial symmetry protected topological order. So these states are in that sense interesting as well. Then again, Rausendorf has done a very interesting work on graph states, and then their ground states of interesting local Pauli stabilizers. Here you only have local Paulis. But now we are interested, and there is some work done on non-local gates in the Hamiltonian as well, and we are interested in hypergraph states, are eigenstates or ground states of non-local interesting symmetric protected topological order, and in this case we can connect them to some coding theory and so on. So I think I talked a lot about what needs to be done, so this is what I have on my fridge at home, that there is still a lot to be done on the hypergraph states. And with this, if you are interested to work on any, or you know a lot about some of these and you have some suspects that it might not work out or might not work, I would like to thank you for your attention, and to my collaborator in Tbilisi and my group remotely to to Ziegen. So thanks.
We have time for questions. I know we had some questions for you.
I don't know much about hypergraph, so this is probably a stupid question, but when you represent a hypergraph and a graph that is both, that has both edges that are graphs and edges that are like collective edges, does it mean that the entangling operations for graphs commute with the entangling operations for hypergraph? Because otherwise,
Yes.
okay.
They're all in Pauli Z basis, so yes, they commute.
All right.
Yes. So it doesn't matter when you apply which gate. Yes.
I think Robert.
Yeah, so I have a question about the stabilizer formalism. So for the 3-qubit hypergraph state, you wrote down the stabilizer generators. But I don't know if they commute, they do not look commute.
They do commute.
Oh, they do?
Yes.
So the group is still that 2 to the n?
Yes.
Okay.
They still commute, and this is the question then which comes in exactly, let's say, in condensed matter, because this Hamiltonian is commuting. And now we are interested if non-local commuting stabilizer always corresponds to hypergraph states. This is also one direction we would like to draw, because there are a lot of interesting topological properties of non-local commuting stabilizer, and we want to find a scheme which shows that it's actually hypergraph state and which hypergraph state it exactly corresponds to.
Thanks.
Any final questions?
Sometimes, quite often, a graph has the same symmetry as a hypergraph, right? And does it mean that what does it say about like the stabilizers of each, like what? Because if you impose like some sort of permutation and it leaves each invariant, that reflects on the nature of the stabilizers.
Well, first of all, I don't know what you call like pictorial. You say pictorial symmetry, right? What kind of symmetry are you?
Permutation.
Okay, permutation symmetry. Well, if you have a permutational symmetric picture, let's say your hypergraph, then also stabilizer is permutational symmetric. So you can, it just permutes the stabilizer in the same way, so it's invariant also.
Okay, but for graphs it's not the case because stabilizers are local and they cannot be.
No, it's the same. It's actually the same exact.
Okay, because it's products. Okay.
Okay, let's thank Mariami again.